today. The plan for today is to do, we've got 7 vocab words that we're going to take notes on, and then we're just going to go a little bit of review on stuff before we go into some visual examples of different types of transformations, and then we will play a little bit of a quiz show game. So for the past like 8 weeks now, we've been talking about linear equations, graphing, systems of equations, stuff like that. We are done with that, at least for a while. So you don't need to worry about y equals mx plus b or anything like that for a bit. We're moving on to transformations. And these are a little bit more fun, a little bit more interesting, and I think a little bit easier. So if you've been struggling a little bit, hopefully this will be a good chance to kind of reset, get your bearings, and get things back together. So I don't know why that's playing like that, but okay. We'll go ahead and get into it. So the first time, or for what we're going to do today, is talk about the different types of transformations. So these are the first 5 vocabulary words. They're written in kind of a funny way, but there's a reason for it that I'll explain in just a minute. The first one is transformation. So transformation in math is changing something, which is usually a point or a shape. It can be a line, it can be a graph, into something else. And there are 4 major types of translation. That's what these are down here. So there's translation, reflection, rotation, and dilation. All 4 of these are types of transformation. So it's a little bit like how a square is always a parallelogram, but not all parallelograms are squares. Yes, Maddie, you'll want to write all of these down. So all translations are a type of transformation, but not all transformations are translations. Reflection, same idea, rotations, dilation. So these are the 4 main types. A translation is taking the same shape or point and moving it on a coordinate plane. So that's like if I have a point that's like right here and I move it over to here, that's a translation. A reflection is mirroring a shape around a given spot, usually an axis. So that's like if I had, let's say a triangle that looked like this on this side of the axis, it'd be flipping it across almost like, so reflection is kind of like if you have a piece of paper. Let me see. It's kind of messy. So if you have like a piece of paper and I drew some really like heavy on ink spot over on one side of it. Was it that just came in? Lana. And then I fold it in half. The shape that would be left as the imprint is kind of like the reflection. You can also think of it like looking at a mirror, but to me, it's a lot easier to think of it as being folded because the shape will flip. A rotation spins the shape around a point, and a dilation changes the size of the shape. So these are the 4 main types of translation or transformations. We'll look at all of them in like visual form in just a little bit, but I want to give you a chance to write down the definitions first. You don't necessarily need to copy them like this in this chart fashion, but hopefully this helps you visualize. These are the 4 main types of transformation. So I'll give you guys a minute to do that. While you're writing this down, I want to remind everybody that today is the very last day that you can turn in the linear equations quiz. If you don't get it finished by the end of the day today, then you will have to do a retake. If you're going to need more time or something like that, please let me know. I can try to extend it, or we could talk about when you can do a retake, whichever one makes more sense. So I'll give you maybe 2 minutes to finish writing these down. Will that be enough time? Okay. Okay, does anybody need more time before I move on? All right, moving on. So the last two vocabulary words are similar and congruent. This is not the definition of similar normally. So if like Mrs. Page asks you what similar means, don't tell her this because it's not the same in English. But in math, similar is two shapes with the same angles but different side lengths. So for instance, if you have a triangle like this versus a triangle like this, these are similar because they're the same basic triangle, but one of them is bigger than the other. So you can think of similar as the same shape but different size. Congruent is two shapes with the same angles and side lengths. So congruent is the same shape, same size. So the definitions are the only parts you need to write down, but if you're actually like trying to determine whether something is similar or congruent, you can think similar is same shape, different size, congruent, same shape, same size. So I'll give you a minute to do this one as well. Then we're going to do a little bit of review on coordinate planes for just a second. I think most of you have those down pretty well, so shouldn't be too bad. Okay. Do we need more time or are we good to go? Okay. I'm not seeing any responses. So if you missed these, we can come back to them later. But I'm going to move on. So let's review coordinate planes really quick. So hopefully you guys all know this is a coordinate plane. We've got two major axes. There's the y-axis, which is the vertical one. There's the x-axis, which is the horizontal one. And then it divides into four quadrants. So we've got quadrant one up in the top right. The quadrants go in kind of a counterclockwise direction like this. So quadrant one has positive x values, positive y values. Quadrant two has negative x values, positive y values. Quadrant three has negative x, negative y. And quadrant four has positive x, negative y. So hopefully you all remember that. We can look at graphing some points to kind of show which ones they're in. So if we graph the point -2, 5, remember when we're graphing points, we always go x, y. So we start by going -2 and then up to +5. So this point is in quadrant 2. Quadrant 2 has a negative number followed by a positive number, and our point has a negative number followed by a positive number. So really quick, what quadrant is 3, -4 going to be in? Quadrant 1, 2, 3, or 4? Yes, Emmy, it's going to be in quadrant 4. Good. So we've got a positive number followed by a negative number. This is positive followed by negative. We can also just graph it. So if we go to 3 and then to -4, that's going to be right here. So that's in quadrant 4. How about -6, -1? What quadrant is that going to be in? Correct, Emmy. Good, Daphne. Good, Camden. Yeah. So this is going to be in quadrant 3. You've got negative, negative. That's negative, negative. And if we graph it, we go to -6, we go to -1. That's right here. So this is in quadrant 3. And then the last one, 3, 2. What quadrant is that going to be in? Yep, good. It's going to be in quadrant 1. So we've got a positive followed by a positive. We go to 3, we go to 2. Yeah, it would be right here. Okay. So hopefully that part's not too tricky for you. You all should know that by now. If you've been graphing lines, then you can graph points. That's a lot easier. So let's look really quickly at transformation notation. And the reason we looked at coordinate planes will make sense in just a little bit. So you don't need to write this down. Just keep this in mind, and there's one line that might be worth writing down for you in a second. So when we perform a transformation of any kind, so translation, reflection, rotation, or a dilation, there's a specific notation for writing the original shape slash point and the new shape slash point. So for instance, if we have a triangle that is triangle ABC, so this is how we would write a triangle with points A, B, and C. We just write it as triangle ABC. The translated version is written as triangle A, and then you've got an apostrophe, B apostrophe, C apostrophe. If we perform a translation on a single point, point F, the translated point would be point F with a little apostrophe. And the way this is pronounced is called the apostrophe in math is called a prime mark. So A with the apostrophe here is read as A prime. So really quick, if I were to give you a triangle that was triangle GFD, what would the translated version be? Or how would you write it? You can skip the little triangle bit. Just do the letters. Anybody? Uh-oh, maybe this doesn't make any sense. Also, if you are going to be writing down any of the lines, I would write down this one. But good, Daphne, that's correct. So we take G prime, F prime, D prime, just like that. That's simple. So yeah, if you're going to write down one of these, you might just want to make a note that any transformed point F would the transformed version is F prime. So whatever the original is, you just add an apostrophe and that's it. If you do like a transformation and then you're going to do another transformation, you can add a second apostrophe. So you could do F prime prime and then F like this. But in general, you usually only want to do one transformation at a time. Okay, so let's start looking at what these transformations actually look like. So this first one right here is a translation. What we did is we took this trapezoid, we'll call it A, B, C, and D, and we moved it. It looks like we moved it down 1, 2, 3, 4, 5, and to the right 2. So we took all of the points on this trapezoid, we moved them down 5 and to the right 2. So this point, since it was A originally, this is going to be A prime. This point, which used to be B, is going to be B prime. This point, which was C, C prime. And this point, which is D prime. So this is a translation. The shape, you'll notice, is the exact same. The shape hasn't rotated at all. It's in the same orientation. It's still facing up. And it's just been moved. In this case, it's been moved to the right 2 and down 5. Okay, so any questions about what translations look like? We'll talk about the math on how to do these tomorrow, but for today, you just kind of want to know what they actually look like. All right, let's look at reflections. So this is a little bit more complicated. Like I said, you can think of a reflection as like if I folded across, in this case, this is the x-axis. So if I folded this across the x-axis, what would the new point look like? So we have A, we have B, C, D, E, and F. So if we took F, right, it's 1 point up, we fold it across, it's going to be just 1 point down. So this right here is F prime. This one is E prime. This one is D prime. There's no points here, but this should be C prime, B prime, and A prime. And one of the nice things about reflections that you can just kind of notice is A prime down here is at -5. A, the original point, was at 5. So this is across the x-axis. If you flipped across the y-axis, you would have the points like this. So you'd have D here, E would be here, F would be out here, A would be way up here, B over here, C, and D, like that. So that would be if you reflected it across the y-axis here. And then you could potentially reflect it across both axes, which would leave it looking like this. So you'd have, and this one you can kind of, there's 2 different ways to flip it across both axes. You can think of it as just flipping across the corner, or you can do flip it one way and then flip it the other. Either one of those works. Any questions about reflections? Okay, 2 more and then we get to our game. So rotations are probably the most complicated. Here we've got a triangle that's been rotated 3 separate times. So let's call this point right here point X. This is X prime, this is X double prime, and this would be X triple prime. So in general, rotations occur around a point. So in this case, it's around the center, the origin. So basically, if you draw a circle, it should hit, with that as the center, it should hit all of these different points. So if we do this with, let's say this outer point is B, if we drew a circle around the center, it should hit here, and it should hit this one. I can't draw a circle, because obviously that's harder than a line. And back to here. And then same with the more inside point. They should all kind of be the same distance away, just at different locations. And in general, rotations only occur at 90 degrees. So you notice that the shape kind of turns each time, right? So like this top point comes over to here, and then comes over to here, and then comes over to here. So it's facing up, and then right, and then down, and then left. And so it kind of just rotates in a circle. Any questions about rotations? All right, and then the last one we're going to look at is dilations. So dilations are just a change in size. You can go bigger. This one is going 3 times bigger. I'll show you how we determine that as 3 in just a second, but you could also go smaller. So what you'll notice here is this first point is at 2, 1, the A value here. This point, A, is at 6, 3. And what you'll notice is both values are 3 times bigger. If you do the same thing with C, C is at 3, 6. The new C is at 9, 18. The B is at, it looks like almost 5, 1. It's a little over, but that's okay. And then B here is 15, 3. So everything's just multiplied by 3. You could also do it the other way around. So you could do it by, or like you could dilate it by a factor of 1/2. So you'd have like your A value here, and then to go up, I don't know, somewhere in here, and back down, and then like this. So that'd be dilating by 1/2. So bigger or smaller is called a dilation. And again, you'll notice there's the same orientation. We have A on the bottom left, C on top, B on the right. They're the same shape, they're just different sizes. So any questions about that one? All right. Well, in that case, get ready, because we are about to start our game for today. So this is a game called What's That Transformation? I'm going to need you all to record your own scores, because there's too many of you for me to do it. So the way this works is you will be asked a question. There's going to be a poll popping up onto your screen. Normal rounds are worth 1 point. Bonus rounds are worth 2 points. So get ready. Let me get the poll ready to go. All right. Are you ready for question 1? The first question, what type of transformation is shown here? You have 1 minute to answer this question. It is worth 1 point. Is it a translation, a reflection, a rotation, or a dilation? So far, we have 10 out of 19 people have voted. 11 out of 19 people have voted. 13. Almost halfway done with your time. If you, for some reason, accidentally click out of the poll, just type your answer in private chat so that I can see that you actually made a guess. Okay, we got 15 seconds. 3 of you still haven't voted. 10 seconds. 5, 4, 3, 2, 1. All right. So we missed 2 people on the votes. This is, in fact, a reflection. Yeah, Camden, I will. Don't worry about it. Reflection here. Now, since this is a reflection, there is a quick bonus question. This bonus question is worth 2 points. Which axis are we reflecting this across? Did we reflect it across the x-axis, the y-axis, or both axes? Also, the plural of axis is like spelled like axes. If you were throwing multiple axes, I think that's kind of cool. Anyway. All right, 14 votes in out of 19. 15 votes in. I'm going to give you 15 more seconds on this one. 10 seconds. If you haven't got your vote in yet, get it in quick. 5, 4, 3, 2, 1. All right. So most of you got this correct. It is, in fact, the x-axis. So we reflected it across here. Whoops. Kind of folded it across this line. So that is a reflection across the x-axis. A reflection across the y-axis, again, would be over here instead. Whoops. Be like this. Come on. Then goes out to here. And then a reflection across both would be down in this bottom left quadrant. All right, moving on. Next question. Question number technically 2. What type of transformation is this one? Is it a translation, a reflection, a rotation, or a dilation? You guys are a lot quicker at voting than the last class was. All right, 16 out of 19. I'm gonna give you, I guess, I'll give you 45 seconds total. 15 more seconds to go. 10 seconds. 5, 4, 3, 2. All right. So this one looks like 82% of you got it correct. This is in fact a dilation. So specifically, we dilated this by a factor of 3. So we took each point, we multiplied it by 3. You can tell it's a dilation because it's the exact same shape, it's just bigger. All right, next round. What type of transformation is shown here? Is it a translation, a reflection, a rotation, or a dilation? Okay. 15 seconds to go. Get your answers in. 5, 4, 3, 2, 1. All right, looks like most of you got this one too. This one is a, did it show up? Hold on. This one is a reflection. And since it's a reflection, we have a bonus question. Which axis did we reflect this one over? The x-axis, the y-axis, or both? Whew, it was a fast 12 votes in, 13 votes in. Got 10 more seconds. 5, 4, 3, 2, 1, and 0. So most of you got this one right as well. This is reflected across the y-axis. So because we folded it across this vertical line here, kind of flipped it, this would be a reflection across the y-axis. All right, I believe we have 2 more questions in our first round, and then we've got the speed round coming up next. So is this one a translation, a reflection, a rotation, or a dilation? This is probably the most complicated one, I think, or the toughest one. Okay, so 15 seconds. I need like a drum roll or like Jeopardy music or something. 5, 4, 3, 2, 1. All right. So most of you got this one correct as well. This is a rotation. So the way you can tell that this is a rotation is that Z to Y, it was on the bottom here. It was going this way. But now it's rotated, so now it's 90 degrees. It went from at the bottom to like this. So each point kind of just goes in like a circle. That's a terrible circle. Oh my goodness. But you get the basic idea. So each one kind of just rotates 90 degrees. And the shape itself rotated 90 degrees as well. All right. Last one of the first round. Is this a translation, a reflection, a rotation, or a dilation? Can't really see the points on the left of this one, but this one would be about where A is and C is about here. 15 seconds. 10 seconds. 5, 4, 3, 2, 1. All right, so this one is a little bit more split, which is the same thing we had last class. It's split between, Aiden, sure, just type it in private chat. So it's split between dilation and translation. This is actually a translation. So you can see that if you look at this one carefully, you see that these shapes are actually about the same size. This one's a tiny bit cut off, so it's a little bit hard to tell. But we moved all of the points up into the right, it looks like. This also should have had primes on these, but whatever. I did not draw this picture myself. So the reason it's not a dilation is A, that the shapes are the same size, but B, we can't do anything to the point -3, -3. We can't multiply that by anything to get +1, +3, right? If these start at -3, -3, it should be the same numbers over here as well if we dilated it. So in general, dilations can't cross the X or the Y axis. All right. The last thing, the bonus round, each one of these is going to be worth 2 points. There are only 4 questions, but you're only going to have 30 seconds on these ones. So the question here is, are the figures shown similar, congruent, or neither? You might have to check your definitions to remember what the difference is between them. Answers are very split so far. You got about 10 seconds left. 5, 4, 3, 2. Get your answers in quick. We're still missing so many. No. Okay, or don't get your answers in quick. All right. So 64% of you got this one right. These are similar. Now, interestingly, these are the same shape, right? They're both right triangles. They have the same angles. This has actually been reflected across the y-axis and dilated by a factor of 3. So this one both got flipped. So the flipped version would have been, I think, like this. It goes down 2. And then it got dilated as well. So this had 2 different transformations happening to it. All right. Are these ones similar, congruent, or neither? And just as a heads up, color does not matter. The last one was 2 points, Maddie. This one is also 2 points. You got 15 seconds left. So eventually, when we're playing this game, I'm going to have like actual prizes or something. But for right now, I'm kind of just testing it out. All right, 5, 4, 3, 2, 1. Okay, so you guys are pretty evenly split this time. It's 60-40. These two shapes are actually congruent. But the way you can tell that they're the same size is if you look at these points, this bottom bit is the exact same. You could also check the height. So this one is just over 13 down to 4, so it's like just over 9. This one goes just over negative 13 to negative 4, so it's also a height of 9. These are equilateral triangles, so they all have angles of 60 degrees as well. All right, and then I think we've got two more. So second to last question, again worth 2 points, again 30 seconds. Are these congruent, similar, or neither? And then for a bonus point in private chat, tell me what two operations happened to go from triangle GEF to G prime, E prime, and F prime. 10 seconds left on the poll. I'll give you a little more time than that on the types of transformations. 5, 4, 3, 2, 1. All right, most of you are starting to figure this one out. These are, these are similar triangles. I'll give you guys a little bit more time. Who could tell me? I see 3 of you have said so far, 4 of you, and have all gotten it right. What two types of transformations happened here to get from the first one to the second one? Also, those of you that said congruent, remember congruent has to be the same shape and same size. Similar means they're the same shape but a different size. Okay, so a few people got this one right. In order to get from triangle GEF to G prime, E prime, F prime, we did first a reflection across the y-axis. So then that would be here. Oops, that was bad, but whatever, close enough. And then we did a dilation. So specifically, this one is a dilation of a factor of 4. We took our 2, went to 8, our 3 went to 12, and then the height of this one went from 1 to 4, and the distance away went from 2 to 8. So again, that is a reflection and a dilation. All right, and then the last question, final round. Are these two shapes similar, congruent, or neither? "15 seconds. Only got 55% of you voting. Oh, there we go. 5, 4, 3, 2, 1. Wow, everybody got this one right, that voted at least. These are neither. So I was hoping to trick at least one person thinking that this was a rotation, but it looks like everybody got it. This is a right triangle, goes straight 90 degrees. This one is an equilateral triangle. Everything is 60 degrees. So good job. That's all I've got for you today. Please tell me what your score was in the private chat before you take off. But there's no new homework for today. Just if you haven't finished the quiz, please make sure to get that finished by the end of the day today before you take off. But otherwise, you guys are good to go. Have a good rest of your day, and I will see you tomorrow. If you do want help on your quiz, please stick around. I'd be happy to help you out.